Welcome, fellow chemists, to the third video in my stoichiometry series. Today we will work on percent yield, and unlike the previous video, there is pretty much one way to do it. But before we get to the how, you may be unfamiliar with percent yield in chemistry, though you certainly know about it. Recall this recipe for chocolate chip cookies from the previous video. I didn't mention how many it serves because that was irrelevant at the time, but this recipe makes 40 cookies. Let's say I tried baking these cookies following the recipe precisely, yet only made 20. At this stage, you probably know exactly where I'm going with this. The topic may be called percent yield, but I feel it's easier to think about it as efficiency. So if I made 20 of 40 possible cookies, then I'm baking at 50% efficiency. I come to that value because efficiency is comparing the actual result and theoretical result. Of course, it's multiplied by 100 in order to express the value as a percentage. Since the result in chemistry is also known as a yield, well, this is where the name of the concept comes from. I'll clarify where we find actual and theoretical yields as we work through a typical question like this. Like limiting reagent, there are two values provided in the question. You may think that since this question clearly states percent yield, that it would be impossible to confuse the two, but not a year has gone by where at least one of my students hasn't made such an error. We all make mistakes, but since the question may not specifically use the words percent yield like this one does, there are other clues you can use to avoid joining that not-so-exclusive club. Limiting reagent questions must provide the amounts of two reactants. Methane is a reactant, but carbon dioxide is definitely not. On the other hand, percent yield questions must provide the amount of a product. However, the question does not always use a word like produces, as this one does, but perhaps made, formed, or created, among others. Once certain you are dealing with percent yield, answering the question starts in a familiar place. That familiar place is a question without a balanced equation and no molar masses. However, I know you have all these values memorized since this is the third video in a row you've seen this equation. With that out of the way, we are ready to use the one and only method of answering this question, which starts with a straightforward stoichiometry grid. But with two values given in the question, which one goes in the top left box? You might already know, but if not, we need to know two things to ultimately answer this question: what should happen and what actually happens. The wording of the question tells us in no uncertain terms what actually happens. The reaction produces 154 grams of CO2. This is the actual yield. As for what should happen, we can now rely on our stoichiometry skills. All along, these answers have been assuming reactants and products behave exactly as the equation indicates. After putting the given 80 grams of methane into the top left box and filling out the rest of the grid accordingly, we get an answer of 220 grams of CO2. This is what should happen and is also known as the theoretical yield. Since we know both the actual and the theoretical yields now, we can use the equation from before. We take the 154 grams and divide it by the 220 grams, multiply by 100, and get 70%. Let me recap what we just did. The 0th step was balancing the equation and finding molar masses. Next, we identified the actual yield in the question and used the other value as a given in the second step for a stoichiometry calculation to find the theoretical yield. The two yields are placed into the formula for percent yield to determine the answer. If your answer is less than 100%, you can feel pretty confident it's correct, but if it's not, you'll just have to work your way back through this list to identify where the mistake was made. Now, what if you did all of that only to find your percent yield is greater than 100? Assuming you did the first three steps correctly, the error must be in the percent calculation itself. That seems a bit obvious because it is, but it's also something I see happen quite often. Instead of 70% for the example problem, an answer 143 is determined by simply switching the actual and theoretical yields. Luckily, this is an easy fix, and I could say you can avoid it by always putting the larger value on the bottom, but there are problems with such a suggestion. First, consider this setup, which results in an answer of 250%. If we flip the fraction over, the percentage is now less than 100. The same is true if I started out with this, too. That's just the way the math works, and it gets us to the second issue. Just because you are expecting and then get a percent under 100, that does not guarantee the actual and theoretical yields you have are correct. And third, who says you can't get a value over 100? I'm not about to present evidence that the law of conservation of mass no longer holds. Instead, I'm going to remind you about two factors that can result in a legitimate percentage over 100 you likely haven't considered: reality and your teacher. If you're working in a lab setting, you may get a yield over 100. While you unfortunately won't win any Nobel Prizes for your work, if the error is not in any of your maths, the error lies somewhere within the procedure. Perhaps something was measured incorrectly along the way, or the final product was contaminated. Explaining away the results in a lab is probably an easier task than dealing with your teacher. Whenever you read a question, look for context clues. While you should not expect a value over 100, the question may use real data in which the previous issues must be considered. Additionally, perhaps the question asks whether the yield itself is reasonable. In this case, if you get a value over 100, you can justify the result as being nonsense with the reason due to some sort of experimental error depending on the scenario. There is one more possibility, of course, but I can't go into further detail at this time. Now that you've seen how percent yield is calculated, how the answer can be checked, and how to potentially explain an impossible result, it's time for you to demonstrate what you've learned. Using the same equation, is it possible for the reaction of 3,200 grams of oxygen with excess methane to produce 1,818 grams of water? Pause the video and give it a go. The mass of water is the actual yield since the question tells us that is what's produced. The 3,200 grams of oxygen is the given which goes in the top left of the grid. Its molar mass is put underneath and the coefficient from the equation goes in the bottom middle. The coefficient for water goes in the top middle with its molar mass in the top right. When the calculation is performed, the result is 1,800 grams of water. You might already know the answer to whether it is reasonable, but let's do the calculation anyway. The 1,800 grams is the theoretical amount of water that can be produced, and the 1,818 grams is the actual amount. When the percent is calculated, it comes to 101%, which is not possible. And there isn't much else to show regarding percent yield calculations, but if you think I missed something, let me know in the comments. The next video will be the last in this series where we will put all of the previous skills to use. Until then, thank you very much for watching.